Myself, Duke Surana, and the topic I'm going to present is sequence detector using flip-flop for pattern recognition. What is sequence detector? It is a finite state machine that identifies a specific pattern or a sequence in a stream of input bits, producing an output when the target pattern is found. It monitors a serial bit stream for a predefined binary sequence like 1011 or 1001. Flip-flop stores the current state of the FSM, enabling step-by-step matching. It produces a high output when the full target sequence is matched. These are the types of flip-flop that are used to detect sequence. Deep flip-flop is most common flip-flop, and the function is given q p plus 1 is equal to d. This predicts the output of the next state, and all the function does the same. It is most common one. JK flip-flop is most versatile flip-flop. T flip-flop very is also used in counters and detectors. SR flip-flop is the most basic one. More and melee machine. More machine more machines output depend on current state, whereas melee machines output depend on state plus input. More machines more state requires larger hardware, whereas melee machines require very compact design. Moore machines output does not contain any glitches, whereas melee machines outputs are generally fast and it may contain glitches. Moore machines output changes with clock edge, whereas melee machines output can change mild clock cycle. Moore machine is used in most textbook example, whereas it is where melee machines are used for timing critical design. This is the step-by-step procedure for finding a pattern. First, we choose the binary pattern to detect. For example, 1011, which will decide on overlap handling. For example, overlapping detection or non-overlapping detection. Second state is state diagram. We have to draw a state transition diagram. Each state represents how much the sequence has been matched so far. It is defined by S0, S1, and so on. Third is state table. Convert the diagram into a state transition table showing current state, input, next level, and output for all combination. Fourth, it is state assignment. Assign binary code to each state. For n state, use log to the base n flip-flops. Choose encoding to minimize logic. Fifth one is flip-flop input equation. Derive excitation equation for each flip-flop using K-map or Boolean algebra from the state table. Sixth is output equation and implementation. Derive the output logic equation. We have to draw the combinational plus sequential circuit and verify with simulation. This is the process of detecting a pattern. S0 is when there is no bits matched. S1 is when one of the bit is matched. Second is now this number increasing the number of bits matching, and this is the table of which shows the process. Overlapping versus non-overlapping detection. Non-overlapping detection after detecting the pattern returns to the initial state of S0 and it does not match any other previous bit. Whereas in overlapping, the previous bits are matched even when we got the pattern. Now this is the real world application of flip of pattern recognition. For example, password locks, pattern recognition, CRC detection, network protocols, UART, FPGA, and all the security where we need some password uses this logic only. Now, the key takeaways from this is FSM foundation. Sequence detectors are built on finite state machine FSM principle with well-defined states. Flip-flop memory D, JK, T, and SR flip-flop stores the state information. D flip-flop is most commonly used. Design methodology. Follow the six-step procedure: state diagram, table, assignment, K-map, equations, and circuit. Overlap matters. Overlapping and non-overlapping modes affect both state count and circuit complexity significantly. It is widely applied from UART to FPGA design. Sequence detectors are fundamental to digital system engineering. Thank you.